Hello everyone, welcome to my channel, The Teaching Show. Please like, subscribe and press the bell icon for more updates. In this series, we are concentrating on the problems on thermodynamics. I have already taken two problems on thermodynamics which I have posted in previous video. So again, in this video, we are going to take two more problems which are based on first law of thermodynamics. So let's get started. So now the problem I'm taking next involves mixing of the contents of two tanks. Okay, so here I have taken helium gas in two tanks, and these two tanks are separated by a valve which is shown over here. Okay, first tank has a volume of 0.1 meter cube and the helium is at 5 megapascals. Second tank has a volume of 0.15 meter cube and it contains helium at 6 megapascal. Now at any instant in time, this valve is opened and these contents are allowed to mix, and we are asked to find out what will be the final pressure in the two tanks. Okay, so let's start this problem. First of all, we will make certain assumptions in order to solve this problem. So it is given in the problem statement that you have to consider the walls of the tank to be adiabatic. What this means is that there is no heat transfer across these walls of the tank. So essentially Q is equal to 0. We have also been asked to take that the walls of the tank are rigid. If I take rigid tank, then the work done is also equal to 0. So Q is equal to 0 and W is equal to 0. We have been asked to take the volume of the connecting line as negligible. Okay, so we have seen Q is 0, W is 0. It is given in the problem statement. Further, these tanks are not moving or anything, so we are going to take a change in kinetic energy and change in potential energy as 0. So now our first law reduces to then delta U is equal to 0. Let's assume that helium is an ideal gas which has a constant CV. What is CV? It is heat capacity at constant volume. Let N1 be the number of moles in tank 1 and let N2 be the number of moles in tank 2. So I'm going to take this as tank 1 and this as tank 2. So N1 will be the moles of helium in tank 1 and N2 is the number of moles of helium in tank 2. Let PF be the final pressure which is reached, and let T be the temperature in the final state. So from first law, what we have seen, the delta U comes out to be 0. Now we know that change in internal energy is given as du is equal to CV dt. Okay, just like you remember delta H or dH, that is given as Cp dt. Delta U or du is calculated as CV dt. So we are going to write delta U is equal to 0. That means the change in the internal energy of tank 1 plus change in the internal energy of tank 2 should summate to 0. So I'm writing change in internal energy of tank 1 as N1 into CV into T minus T1, and the change in the internal energy of tank 2 as N2 into CV into T minus T2, where T is the final temperature and T1 and T2 are the initial temperatures in the tank 1 and tank 2 respectively. So on rearrangement, we get N1 plus N2 into T is equal to N1 T1 plus N2 T2. Okay. Now since we have been asked to take helium as an ideal gas equation, we are going to apply the equation of state for ideal gas, that is PV is equal to nRT. So instead of NT, I'm just going to write PV by R, R will get cancelled throughout. So what I'm left with is P into V1 plus V2 is equal to P1 V1 plus P2 V2. Now we know what are the initial pressures. We know the initial volumes. So I can just rearrange this equation to find out what will be the final pressure. Okay, just substitute these values and get the value of pressure in the final state, which comes out to be 5.6 megapascal. Easy? Good. So now let's start with problem number 4. This is a slightly bigger problem, but it covers a lot of concepts. Okay, so I've combined more than one concept in this problem. So just listen to this problem carefully. Okay, so let's just go to the figure and understand this problem first. This black portion, it is the piston, and I have the cylinder which is shown by blue color. Okay, so in the start, your piston is at one end of the cylinder, and the cylinder is filled with a mixture of saturated steam and saturated water at 150 degrees centigrade. It is given that the mass of water inside the cylinder is 0.91 kg and the volume of this total cylinder is 0.283 meter cube. We are assuming that the volume occupied by the piston is negligible. Okay, so this is our initial state. Now, at any instant of time t, what we are doing on the other side of the piston, like this side of the piston, we are connecting this to a constant pressure line which is carrying air at a pressure of 1400 kilopascal and at a temperature of 15 degrees centigrade. So this air is introduced into the cylinder on the other side of the piston using a throttle valve. Okay, so this is the problem of charging of a cylinder. You might have read this before. So basically we are filling this part of the cylinder with air which is at 1400 kilopascal. Okay, now this air is being filled until the pressure inside this compartment becomes equal to the pressure which is in the constant pressure line, that is 1400 kilopascal. Okay, so as the air gets filled, what happens? The pressure over here is high. It pushes this piston, and so some work is being done by air on this piston, or we can say some work is being done on water. Okay, so some work is being done W, which we have to calculate. We have to calculate what is the final temperature of the air inside the cylinder and what is the volume which is occupied by air. Okay, further we are going to assume that water is undergoing a compression which is simply a reversible adiabatic compression. So when I am saying reversible adiabatic compression, that means Q is equal to 0. So as we had seen in the previous video, that if it is a reversible adiabatic process, then dq is equal to 0. That means from Clausius equality, we have for a reversible process, ds is equal to dq by t. So if dq is 0, then ds is equal to 0. So what we are saying is that the compression of water is a reversible adiabatic process. That means it is an isentropic process. So the entropy of the water in the initial and the final state remains the same. So we have now understood the problem. Okay, now there are certain assumptions we have to make. Okay, so what assumptions we are making? We are assuming that cylinder is well insulated and so no heat transfer takes place from the boundary or across the piston. Okay, second thing we have discussed that wet steam, it undergoes a adiabatic compression. Third is that air has to be taken as an ideal gas and its specific heats are constant. Okay, and further we know that for an ideal gas, du is equal to cv dt and dh is equal to cp dt. But for the charging of a cylinder, we have seen that change in the internal energy of the control volume, that is equal to the enthalpy of the or I should say the internal energy of the control volume, that is equal to the enthalpy of the air in the main line. Okay, so we will use that concept. So we are going to neglect volume occupied by the piston for sure. So let's start with the problem. So first I am going to concentrate on the air which is getting filled into the cylinder. So taking the energy balance on this part of the compartment in which air is getting filled. Okay, so now my control volume is this part, okay, where air is getting filled. So change in the energy of the control volume, that should be equal to the enthalpy of the air which is coming in across this control surface minus the work which is being done by this air. Okay, so that's what I have written. The change in the energy of the control volume per unit time, that is equal to the enthalpy of the air which is coming inside the cylinder minus the work which it is doing on the piston. Okay, we are neglecting the change in the kinetic and potential energies because your cylinder is not moving. There are no changes in the velocities and all, no change in the datum level. So it's perfectly fine to take the change in kinetic energy and potential energy as 0. Now integrating between initial and final states, what we get is that M2U2 minus M1U1 is equal to MI/HI minus W. Work done by air in compressing the steam is denoted by W. Initially there is no air in the cylinder, so M1 is equal to 0, and whatever the mass which is there in the cylinder in the final state, that is the mass which is entering through the wall. So M2 is equal to Mi. Now M2 can be given by ideal gas equation, that is P2V2 upon RT2. Okay, so we just put all these values in this energy balance, and then we get the equation as M2U2 is equal to M2HI minus W, where M2 is given by P2V2 divided by RT2. So this is your equation. We are going to use it again. Okay, now let's focus on the energy balance for steam. For energy balance of the steam, because it is undergoing an adiabatic process, there is no heat loss, so change in internal energy is equal to the work done. Adiabatic process, so we have discussed delta S is equal to 0. Since we do not know what is the quality of steam in the initial state, so we are going to find out first what is the quality. Okay, so initially we know what is the volume which is being occupied by the steam. It is 0.283 meter cube. We will find out what is the what is the mass. We know it is 0.91 kg. So we will find out first what is the specific volume. Okay, so 0.283 divided by 0.91, it comes out to be 0.311 meter cube per kg. Okay, now we are going to use this value because okay, initially your steam is at 150 degrees centigrade because it is a mixture of saturated steam and saturated water, so it is at saturation temperature. Go to the steam table corresponding to the saturation temperature of 150 degrees centigrade, read the values of specific volume of gas and of liquid. Okay, then use these two to find out what is your X1, which comes out to be 0.7918. So initially you have 79%, about 79% of water vapor and 21% of water, liquid water initially in the cylinder. Okay, once we know X1, I can also go and read the values of internal energy and entropy from the steam tables at 150 degrees centigrade. I use this and my quality of steam to calculate what will be the internal energy and entropy initially. Okay, now in next part what we are going to do is that since this is an isentropic process, nothing is changing, entropy is not changing, so entropy in the final state is again same is the initial state, that is 5.797 kilojoules per kg, which I will use in order to calculate what is the quality of steam. Okay, so in the final state we know the pressure. Okay, so the pressure of the steam will be equal to the pressure of air, that will be equal to the pressure of line, so it is 1400 kilopascal. I will use this value, go to the steam table and find out for this pressure what is the entropy of the gas and the liquid water. Okay, then I will use these to calculate my mole fraction, to calculate my quality of steam, which is X2. Okay, so now I know X2, I can calculate what will be the specific volume of the wet steam and the internal energy of the wet steam in the final state. Once I know what is the change in the internal energy, I can calculate, because now I know internal energy at the initial state and the final state, so I can easily calculate what is the amount of work which is being done. So I can calculate it. Volume occupied by air, that is equal to V cylinder minus the volume which is occupied by the steam. It is equal to the specific volume into 0.91, that is the mass of the steam. Okay, so I can also calculate what is the volume occupied by air. Finally, now I know most of these or all of the unknowns in this equation which we first saw. I am going to plug in all these values and find out what is okay, V2 also I know, yeah, so I can plug in all the values and find out what is the final temperature. So thanks for watching this video, and please like and subscribe to my channel. Thanks a lot.